Okay, so last week, Wednesday and Friday, we talked about dosage calculations. We went over the three methods with the formula, the proportion, and the dimensional analysis or unit conversions. And then, of course, on Friday, with the IV, drip rates and stuff like that, we saw that the simplest method to use really is that dimensional analysis or the unit conversion, just because in those problems there can be 4 or 5 different levels of conversions that have to take place. And the dosage formula, while it would work, would be pretty hefty. Today, we're going to talk about 2 other types of dosages, still basically going off the dosage formula or the dimensional analysis for what we do. But the first one we're going to talk about is dosages based on weight. Now, I've already talked several weeks ago about the difference between weight and mass. Excuse me. And here's where the blurry line between the two of them get blurred even more, because we use pounds in the standard system, which really is a weight, but we're going to end up using kilograms in the metric system, which really is a mass. And we're going to convert between the two of them. The big thing to remember here, 1 kilogram equals it's technically 2.208 or something like that, but we're just going to use 2.2 pounds. So a bit of a reminder of that calculation. If someone comes in with a stated weight of 100 and, so let's say we have a patient that comes in at 154 pounds. To find their weight, or in kilograms and metric, technically what we would do is put this over 1, and we would multiply by a conversion factor, where pounds go on bottom and kilograms on top. 1 kilogram is 2.2 pounds. The pounds will cross cancel out. 154 times 1 kilogram is 154 kilograms. 1 times 2.2 is 2.2. So what we end up doing here is simply dividing by 2.2. We get 70 kilograms. Well, this is a conversion that we use often enough, kind of like inches and feet, where we don't want to have to go through a formal unit conversion like this. So whenever we see a weight given in pounds, we can just go ahead and divide that weight by 2.2 to get kilograms. So then back to dosages based on weight. We might have an order for an appropriate dose of a medication where the label says 200 milligrams per kilogram per day. And let's say our patient comes in with a weight of 132 pounds. So our first step in any of these problems that are based on weight is to convert our weight, if given in pounds, convert it into kilograms. So we're going to divide by 2.2, which should give us 60 kilograms. Let's double check it. And of course it does. Now with these, the next step is one of the few places where we cannot use the unit conversion or dimensional analysis. We must use, well, we could use the unit conversion, but it makes more sense to use a proportion here. The proportion says the dosage, 200 milligrams per kilogram per day. We're going to ignore the per day for now and just use the 200 milligrams per kilogram. That's 200 milligrams per 1 kilogram. And we want to know how many milligrams that would be for 60 kilograms. And again, we're looking for milligrams of medication. So this is how we know that this is a proportion and not a unit conversion, because none of the units are changing here. On the left side, we have milligrams and kilograms. On the right side, we have milligrams and kilograms. So we're not changing our units, we're just changing the numbers. Kilograms go from 1 to 60. We need to now adjust the milligrams. So we cross multiply 200 times 60 kilograms divided by 1 is 12,000 milligrams. Now, the 12,000 milligrams, now we have to bring in the time that was per day. Well, let's look at another similar problem. Let's say that the label tells us that you should administer 0.4 milligrams per kilogram per hour. The patient that walks in the door is 99 pounds. So once again, we need to convert that into kilograms. We're going to divide it by 2.2. Gives us 45 kilograms. Now we can use that for our dosage. We have 0.4 milligrams per 1 kilogram. Again, for now we're going to ignore the hours, but we need to keep track of it because we will need that in just a second. We want to know how many milligrams that would be for a patient who is 45 kilograms. So we're going to cross multiply and divide. 0.4 times 45, I believe it's 18, but I'm going to double check. It is. Divided by 1, of course, gives us 18 milligrams of medication. Now, to double check, we have to look. That was per hour, so this is 18 milligrams per hour. Well, let's get a little more complex on this. Let's say that we have orders for the appropriate dose. We can call it standard dose. To be administered. I'm not going to get into the abbreviations here. You know, it could be a Q4H or whatever. We're going to say administered every 4 hours. So that would be a Q4H if we were actually using the medical abbreviations, but we're going to keep those out of it for now. And let's say that the label says that it should be, what do I put in there? Let's go 30 milligrams per kilogram per day. So, first thing we're going to do is we're going to look at our patient. And let's say that this patient is 88 pounds. So we're going to convert that into kilograms by dividing by 2.2, giving us 40 kilograms. And we do our proportion, 30 milligrams per 1 kilogram equals how much for 40 kilograms? We cross multiply and divide, we get 1,200 milligrams of medication. Now that is, again, going back to the dosage, was per day. Don't make the mistake of saying for every 4 hours. The doctor wants us to administer a dosage every 4 hours. But the actual daily dose is 1,200 milligrams. So that is 1,200 milligrams per day. 1 day, I'm not going to even bother doing the unit conversion. 1 day is 24 hours, so I'm just going to put in 24 hours. And now we have to figure out how much would that be for 4 hours. So once again, we're using a proportion because we're looking at milligrams and hours here. Over here, we're also looking at milligrams and hours. So we'll cross multiply. 1,200 times 4 divided by 24 gives us 200 milligrams. And that is every 4 hours. Now those times are very important to keep track of, as we're going to see in a little bit when we talk about safe dosages. For right now, let's take a look at what we call, let's do a simple safe dose. Let's say the doctor's order, they want 10 milliliters of Tylenol 3 every 4 hours. Patient weighs 55 pounds. Label on the bottle states 12 milligrams of codeine per 5 milliliters of fluid. You look up and you find that the safe recommended dosage, now the active ingredient here that we're looking at would be for codeine, is 1 milligram per kilogram every 6 hours. So what we're going to do here is we're going to figure out what actually is the dosage here that the doctor is recommending, and then what actually is the safe dosage. So we'll start out 10 milliliters every 3 to 4 hours. Well, 10 milliliters. Actually, let's go the other direction. Let's do the safe dosage for this patient first. So we keep it consistent. We got the weight in pounds. We're going to convert that to kilograms. We're going to divide by 2.2. Gives us 25 kilograms. So we have a patient that is 25 kilograms. A safe dose of 1 milligram per kilogram. Again, we're going to keep that 6 hours to ourselves. We're going to use it again later. We want to know how much that would be for 25 kilograms. Well, cross multiply and divide is pretty obvious. That's going to come up with 25 milligrams. Well, 25 milligrams is going to be how many milliliters? We're going to take 25 milligrams, put it over 1, and we're going to multiply. We know that put milligrams on bottom, milliliters on top. We're told here that 12 milligrams in 5 milliliters. So the milligrams cancel out. 25 times 5 is 125 milliliters. 1 times 12 is 12. So 125 divided by 12 is going to give us 10.442 basically. 10.42 milliliters. Looking at that at first, well, that looks good. This is 10 milliliters. We can safely administer up to 10.4 milliliters. So it looks good. But we've got to remember the time off the recommended dose. This is per 6 hours. The doctor's recommendation was 10 milliliters per 4 hours. So we need to convert this from 4 hours to a 6 hour dose. Now we're not trying to change the units here, we're trying to change the numbers, but we can still do basically a dosage calculation on that. So if this is 10 milliliters per 4 hours, how much would it be per 6 hour? Well, we're going to do that as a proportion because we're not going to change the numbers. It's still going to be milliliters and hours going to milliliters and hours. We're not going to change the labels, I should say. It'll still be milliliters and hours going to milliliters and hours, but we're changing the numbers, going from 4 hours to 6. You cross multiply and divide, this becomes 15 milliliters every 6 hours. So what the doctor has recommended to us is the equivalent of 15 milliliters every 6 hours. Safe dosage is no more than 10.42 milliliters every 6 hours. This is not a safe dose. You might be thinking to yourself, Well, the doctor made the order. If I give the doctor's orders, it's not my problem. In the medical field, anybody who comes in contact with the medication is liable for double checking the dosage. So that means the doctor is liable for giving the correct dosage. The pharmacist is liable when they fill the prescription for making sure that dosage is correct. And the nurse or whoever measures out the dosage and administers it is also reliable for double checking that dosage before it is administered to a patient. So if you've had any part in that string of the medication, you have to double check that dose and make sure it's correct before you pass it along to the next person on the list. Well, the next step, we're going to look at dosages based on body surface area. You might be wondering what possible dosages. Well, first of all, what is body surface area? Well, body surface area is literally what it sounds like. It is literally the area of the skin on the body, the human body that you're looking at. Now, so you might be wondering, well, why would we ever want to do a dosage based on body surface area? Well, the most common situation where we do a dosage for body surface area would be for burn victims. The medication for healing the burns and other things, stopping blood toxicity and things like that, is based on body surface area and also the percent of the surface that is burned. Other ones might be skin conditions like eczema and rashes and things like that. Some of them go based on weight, some of them go based on body surface area. So there are two ways to calculate body surface area. One is a formula. Being a math geek, that's where I'm going to start out, is the formula. Two is something called a nomogram. A nomogram is that chart you saw me pull up there just a second ago. It's a way of graphically estimating the body surface area. But we will find that it's not, it's accurate enough, but it's not totally accurate. So anyway, let's start out with the formulas. Let's say we have standard measurement. In other words, the height is in inches, the weight is in pounds. For standard measurement, the body surface area, BSA, which is always given in meters squared, is the square root of the height in inches times the weight in pounds divided by 3,131. The 3,131 is just a constant that has been found to be the best estimate of body surface area through the years. Of course, any of these formulas are just estimates because everybody is shaped differently based on height and weight. This is never going to be exact. Fingers and certain other parts of the body may not have much weight, but being a little bit longer can drastically increase body surface area. So obviously there's no way to exactly do it without actually literally having the patient there and doing a pretty complex procedure to estimate body surface area. So anyway, let's say that we have a patient that is 5'4" tall and 140 pounds. So to plug this into our formula, it is the square root of, first of all, 5'4" has to be converted into inches. 5 feet, 5 times 12 is 60, so plus 4, that is 64 inches, times 140 pounds, divided by 3,131. I'm going to assume at this point all of you understand the order of operations and know how to punch this in your calculator. So just a second, square root, 64 times 140 divided by 3,131. Many of you would have to close parentheses on your calculator if you're not using a graphing calculator. Otherwise, in the graphing calculator, it just puts it right in the square root. Hit square root, we get 1.69. That's square meters. On body surface area, we almost always go to 2 decimal places. So that particular person has an estimate of 1.69 square meters of body surface area. if we have a patient that is measured in metric, or if their statistics are measured in metric. So in the height is going to be in centimeters and the weight in kilograms. The formula becomes, again, the body surface area is still given in meters squared. They're going to have a height of, let's say they have a height of 130 centimeters. Oops, sorry. Let's come back and do that. I give you the formula first. It's height times weight again, but this time the constant changes. The constant we're going to divide by is 3,600. So the difference between the 3,600 and the 3,131 is just the conversion between inches and centimeters and pounds and kilograms. Really, it's remarkably close between the two of them cancel each other out. So anyway, now let's say we have a patient who has a height of 130 centimeters and a weight of 70 kilograms. Body surface area is going to be 130 times 70 divided by 3,600. So second square root. Gives us 1.53 square meters of body surface area. So let's compare these to our other method. The other method was the nomogram. The nomogram is this thing right here. I'm going to enlarge it just a touch. And I'm going to add a line here that we're going to need. There we go, format. We're going to make it a little thicker. Or make it red so it shows up better. Hopefully that shows up well enough on your screens. It looks like my color is not transmitting real well today, but hopefully it's close enough on your screens. So let's look at our first patient here. This first patient was measured in inches, 64 inches tall, and 140 pounds. So on our nomogram, over here, this is the height on this far end. We're going to go to 64 inches. There's 60, 65, so 64 would be right there. And 140 pounds. Now you can see on the weight only goes up to 180 pounds. So anybody over that, we can't use the nomogram anyway. 140 pounds is right there. So our 140 pounds are over there. So the weight is over on this far right side. The BSA, or body surface area, is given in this column right here. So we look to see where that crosses. That's 1.7 here, so it's between 1.7 and 1.8. Actually, between 1.7 and 1.75. Looks to me like it's more like closer to the 1.75, so I would say maybe 1.73. Well, let's go back to our calculation here. Our calculation was 1.69. So the nomogram tends to always slightly overestimate the body surface area. We'll see in the next example, or the metric example, it does the same kind of thing. So the calculated value is 1.69, the nomogram is 1.73. So let's look at this one. Patient's 130 centimeters and 70 kilograms. So back to the nomogram. Erase that. Take our line. So we said, what was that, 130 centimeters? So 130 centimeters, we're going down here. There's 130. There we go. And we said how many kilograms? Wish I had a memory. 70 kilograms. So 70 kilograms goes up to here. That's lined up with the 70 now. And on the body surface area here, we see it's between 1.65 and 1.7. Pretty close to right in the middle, so 1.67 or 1.68. I'm going to go with 1.67 since I know this almost always overestimates anyway. Oh, just lost my Word documents. Darn it. We'll get this one up, and we'll do an auto recover. There we go. Get back down to where we were. So we just said this came out to about 1.67. Again, I went with the lower number, even knowing that this always tends to slightly overestimate. We can see 1.67 square meters is quite a bit more than what the calculated value was. So the nomogram does have its weaknesses there. One of the other weaknesses our nomogram has, you can see here, not too many people over 90 inches tall. I mean, 7 feet is 84 inches. So really 6'8" is 80 inches. You shouldn't ever need to go above that, really. The other side here, however, only goes up to 80 kilograms or 180 pounds. There are a lot of patients out there that are over 180 pounds. So you can't use the nomogram for them. The nomogram is basically used for children. We're going to do a few more examples from height and weight here in a minute, but for right now, I want to show you this part. This piece here is actually a separate table in itself. It's in a box of its own. Is really not connected to the rest of this table, this nomogram, at all. What it is saying, the term is height and weight proportionate. If we have a patient, a juvenile patient, that is height and weight proportionate, this little chart gives us their body surface area rather quickly. So for example, let's say that we have a juvenile patient, a child that weighs 68 pounds. The nomogram allows us to do this quite quickly. Now we have to double check here just to make sure. And yes, the weight is in pounds, and this is in square meters. So we said 68. Well, here we have 60, 65, and 70. So 68 should be in between there, slightly closer to the 70, which puts us right here, between the 1 and the 1.1, actually between 1.05 and 1.1. I'd say really close to being right between it. So 1.07 or 1.08. Well, let's say 1.07. So 1.07 square meters of body surface area. Well, let's go back and say that this person this child is 68 pounds. Let's say that their height is 4 foot 1 inch. Actually rather tall for a 68 pound child. Let's now go back to the nomogram. Of course, this is 49 inches. And let's find them using the full chart. So height in inches. I got to put my line back in here, it looks like. We'll just get it put in first, and then we'll adjust it from there. Okay, so there we have it. It said 49 inches. So it's 40, 50, 49, or 45. 49 would be somewhere in there. So there's 49. And we said 68 pounds. So 68 is going to be, there's 60, there's 70, 68, somewhere in here. This looks actually relatively close. It's coming out to 1.02, maybe even slightly below 1.02. So that portion of the nomogram is giving us 1.02 meters squared. The other one gives us 1.07 meters squared. Let's look at the formula. So 49 inches. So the body surface area is going to be 49 inches times 68 pounds. This is standard unit, so we're using 3131. So square root 49 times 68 divided by 3, 131. Getting 1.02. So the smaller the child is, the closer the nomogram is. You can see really close there, actually almost exact. The little cheater chart is a little off because this child's actually a little bit small for their height, so it didn't quite come through quite as well. But anyway, you get the picture as to how those are both used. So now let's go back. Let's say we have a patient that is 61 inches tall, weighs 123 pounds. The doctor orders let's say they order let's do this. Let's say they order 80 milligrams of medication to be administered. And let's say the label on the bottle says up to 30 milligrams per square meter of body surface area. So let's do a quick calculation of body surface area. I am the math geek, so I'm going to use the formula. So 61 times 123, of course, divided by 3131 again. Gives us 1.55 meters squared of body surface area. So now we're going to take this label here to figure out what the safe dose is. 30 milligrams, and we're going to use a proportion just like we did for weight. 30 milligrams for 1 meter squared. We want to know how much that is for 1.55 meters squared. If you haven't noticed by now, obviously the doctor's dosage is way off. We cross multiply and divide. We're going to get 46.5 milligrams is the safe dose for this patient. The doctor had ordered 80, so they're way off on their dosage. Any questions? Okay, so the last thing we're going to mention is something called a titration. Titration comes into effect when we have a dosage that's given as a range. Let's say that we have a label that states that the safe dose is 1.5 milligrams to 2 milligrams per kilogram per 8 hours. What is the allowable range of dosages then for a patient who comes in with a weight of 176 pounds? Well, first step, since this is given in kilograms, this has to be changed to kilograms. We divide by 2.2, we get 80 kilograms. So, we can pick either one, either the minimum or the maximum dose. Doesn't really matter. I'm going to use the maximum dose. 2.0 milligrams per 1 kilogram. Again, ignoring the time for now, but making sure we keep track of it for later. 8 hours. How much is that for 80 kilograms then? We cross multiply and divide, get 160 milligrams. So that's 160 milligrams per 8 hours. To find the minimum dose, we can go through the calculation again, or we can use a titration. The 160 milligrams was for using the maximum dose, the 2.0. Just like we did with the dilutions, we know this number is going to get smaller, so we use a ratio of 1.5 for the minimum dose to 2.0 for the maximum dose, and we can multiply. Again, this is multiplication, not a proportion. We're multiplying straight across. We can cross cancel. The 2 and the 160 get 80. So 80 milligrams times 1.5 is 120 milligrams. So this, and of course that's still per 8 hours. So the safe dose for this patient is between 120 milligrams to 160 milligrams every 8 hours. Okay, we only have about 5 minutes left, so let me give you some homework pages. In the book, page 184, 1 through 11, the odd, goes through the titrations. Page 188 through 190, 1 through 21, the odd, goes through dosages based on weight, and also on safe dosages, 196 through 197, 1 through 19, the odd, goes through the dosages and safe dosages for dosages based on body surface area. That pretty much concludes Unit 3. On Wednesday, we will talk about, we'll just do a bunch of examples of dosage calculations because that is kind of the big climax of the course. Next week, on Wednesday, we will be having our Unit 3 test in class. So next Friday, we should be starting our first set of material for Unit 4. So with that, we'll cut her off 4 minutes early here. You guys